Thank you very much. I am pleased to be here. I'll be talking to you about quantum locality, unification, cost, and consequences. It is, doesn't seem like it's moving. Okay, I need to click. Perfect. So it's actually, most of the ideas I'll be presenting come from my paper in the Proceedings of the Royal Society, The Cost of Quantum Locality. Yeah, quantum locality, that's the first idea that I want to explore with you. It's of course in sharp contrast with the most famous expression, non-locality, that we still hear a lot in the field of quantum foundations. Perhaps a bit less in this sub-community, but a lot in quantum foundations, which for some reason people still equate to violation of Bell inequality. Now, I think a cat should be called a cat, and violation of Bell inequality has nothing to do with non-locality. Bell theorem is a statement about the unsuitability for classical pieces of information to account for quantum phenomena. And the logic is, if one insists that quantum phenomena should be explained by underlying classical pieces of information, then one will have to retreat into a bad explanation. And non-locality is anyway just one such kind of bad explanation. But the kind of non-locality that I'll be referring to is echoing Paul's talk yesterday and also Vladko's talk today, is more what we could hear, or I put quotes, I'm not quoting anyone in fact, but some sort of non-locality in the formalism. What I mean by this, you all know these famous states which do not admit a factorized descriptions, entangled states. And then I'll make the case more precise, because if Alice and Bob share such an entangled state, one can still say, well, we have local descriptions. It's given by the reduced density matrices, right? And it's local really in the sense that I'm advocating here. In fact, it's according to Einstein's criterion of locality, namely the description of system A is independent of what is done with system B, which is spatially separated from the former. That means that if Bob plays with his system, it may affect his own description, the row B, but it will leave invariant Alice's description. It's indeed the case for a reduced density matrix. But the problem is that then we've thrown away too much information if we take that to be the description of systems, because it's not complete, meaning that we can no longer recombine the descriptions and hope to be able to predict the distributions of any joint measurements that Alice and Bob would like to perform on their recombined systems. Okay, or in more technical term, all distributions that can be observed is encompassed by, say, the global density matrix, but then it's too late. If we've traced out over the systems and we've got row A and row B, we can no longer retrieve the global density operator. So then we go like, oh, well, there's also the option of describing stuff with the global state vector. So Alice can choose to have as her own description of the system, the global state vector, and so does Bob. If that's the case, then we will find a complete description. Of course, they can put their descriptions together. They gain nothing by putting it together. They already had it. They'll be able to retrieve the global density operator. But then it's no longer local in Einstein's sense. Why? Because if Bob happens to play with his qubit, then he will affect his own description, no problem. But the problem is that he's also affecting Alice's description. And it seems to be like there's a non-local effect. Again, if we take that both Alice and Bob choose to describe their individual system by the global state vector. So many people still think that we are stuck in a dichotomy, that description of entangled system can be either local or complete, and we kind of have to choose depending what we're interested in. And that definitely poses a problem. But this dichotomy has been proven false more than 20 years ago by Deutsch and Hayden. So to make the case clear, they exhibited a description for Alice, QA, and a description for Bob, QB. It's in fact called the descriptor of Alice's system, such that whatever Bob does to his system will affect his own description. That's fine. Of course, it's fine. But it will leave invariant Alice's description. And moreover, if you have QA and QB in your pockets, then you have all what you need to retrieve the global density operator. And so you're able to predict the distributions of any measurements made on the system. Now, that's my Google screenshot of information flow in entangled quantum systems, the paper by Deutsch and Hayden. And one of the problems that I've tried to address lately is I was quite puzzled by the fact that it's been only cited less than 200 times in 20 years, in more than 20 years. And it wouldn't be a problem if it was just a regular statement, but for the importance of the statement, this to me was an indication that it was either unappreciated or ununderstood. So I wrote a pedagogical approach to the paper recently, and I'm quickly advertising it if anyone cares to learn a bit more how and why descriptors, Deutsch-Hayden descriptors work. I basically put in 20 pages or in 15 pages what is explained in a more concise way in the Deutsch-Hayden paper. Now, in what follows, I will try to give you just the A of the ABC, perhaps. So, yeah, in a sentence, Deutsch-Hayden descriptors is the investigation of quantum computational networks in the Heisenberg picture. Now, why quantum computational networks? Well, they have universality properties which enable them to simulate any other system. So although it looks like a very specific system, it's in fact very general. And I even take it, so it's going to be an n qubit system, and I take all the qubits to be initially in the state 0. So 0 tensor n is in fact, I just call it 0. They're all say spin up. We call that ket 0. And we are well, I actually was much more familiar with the Schrödinger picture. That's how I learned quantum theory. And in the Schrödinger picture, so we have this initial state, ket 0, the unitary evolution that describes the dynamics of the network will act this way on the state, and that gives us the state at time t, psi of t. And if later on we're interested in computing stuff like expectation values of some observables, or what's the probability of measurement outcome 17, whatever, we will end up doing such a calculation, a sandwich-like calculation. But in the Schrödinger picture, that's the object that describes the theory, essentially. And then we're equipped to later on compute those expectation values. In the Heisenberg picture, well, the idea is just that the evolution operators act on the observables. And so the observable is going to be evolved to, I denote it O of t. It now depends on time because the unitary operator here describes the dynamic between time 0 and time t. Now, in the Heisenberg picture, at first sight, we seem to be in an awkward stance because it doesn't have the property of the Schrödinger. It seems not to have the property of the Schrödinger picture that we don't need to know in advance which observable we care to measure or to compute its expectation value. You know, in the Schrödinger picture, we evolve psi of t, and if ever at one point we're like, oh, I'd like to know the expectation value of such an observable, we then do the sandwich calculation. Whereas here, it seems like I need to know right at the beginning which observable am I going to be interested in. But the idea of a Heisenberg picture description is to encode in one object the expectation, not the expectation value, the observables, the time-evolved observables for all observables. So at first sight, one may ask, well, does one need to keep a table of the evolution initial observable to observable evolved for all possible initial observables? That would in fact be terrible because such a table is uncountably infinite. And the answer, fortunately, is no, because a basis suffices. So if an observable at time 0 can be expressed as a linear expansion of some basis operators, BIs, well, then its time-evolved counterpart by linearity is just going to be the same linear combination, but of the time-evolved observables, BIs. And in the case of quantum computational networks, well, a very convenient basis is the, let me call it the Pauli basis, with sigma mu's for each qubit tensored out, with mu's running over 0 xyz. Sigma 0 is taken to be the identity operator, sigma xyz, the Pauli operators. But we can do even better. We can take, instead of a basis, we can take a generating set. And that's actually a crucial idea. So instead of here I have 4 to the n operators that I would need to track their evolution. Instead, it can be reduced to 2n operators, these ones. Sigma x, tensor 1, 1, 1, sigma z, tensor 1, 1, 1, 1, tensor sigma x, tensor 1, 1, 1, and so on. And call this one q1x of 0, q1z of 0, q2x of 0, and so on. Now, these two together, they can be encompassed in a single object, a vector of 2 component. That's why it's bold font, q1 of 0. And then it evolves in time by just the way observables evolve in time, with the sandwich by u. Now, this object is the descriptor of qubit 1 at time t. And if we want to talk about the descriptor of the whole network, well, it's simply the collection of all descriptors of each qubit at time t. Let me call it the global descriptor. It's important, the reason why it works is because the multiplicative structure of the generating set is preserved. What I mean by this is that I've argued that any observable can be expressed this way, but then I reduce this to this way. So for instance, if my 5th basis element was sigma x, tensor sigma z, tensor identity, then I can realize, oh, well, by the multiplicative abilities of these guys, I can generate B5 by, yeah, in this case, it's just Q1x of 0 times Q2z of 0. And then if I wonder, well, what's the time evolved counterpart of B5? Well, that's it. And by inserting the identity here, I get that the time evolved counterpart of B5 is the same prescription, but instead with the descriptors evolved in time. So that remark makes it that, allows me to state that, so the idea is that any observable at time 0 is in fact a polynomial of 2n operators. So, you know, with those operators, I multiply them and then I get a basis and then I sum them. So that gives me a polynomial. And if I want to investigate the observable at time t, well, then I keep the same polynomial, but I apply it to the time evolved observables of the generating set. That's the A of the ABC of Deutsch and Hayden descriptors. Now, let me move on to Raymond-Robichaud's approaches. So more recently, much more recently, Paul Raymond-Robichaud came up with 2 other approaches to quantum locality. And for the purpose of this talk, I'm going to be interested in how do they instantiate in the case of a quantum computational network. Now, a first approach is called the evolution matrix. Here I'm specifying of qubit k. So I'm just going to go quickly about how it's defined for qubit, a generic qubit k here. And it's defined this way. So it's a 2 by 2 matrix. I and j run over the values 0 and 1 because it's a qubit. And the matrix elements will be of the form this. And so this is in fact an operator acting on the whole Hilbert space, U dagger times another operator here times U. And this should perhaps ring a bell when I spoke of generating set of the algebra of observables in the Heisenberg's picture. Well, the idea behind evolution matrices is instead to take the Pauli basis, to take the canonical matrix basis, and have as a generating set these guys. There's 4 n operators here, which if I multiply them together, I can generate a basis. And so these 4 will be the 4 elements that are attached to the evolution matrix of qubit 1. By taking a sandwich with U dagger and U, I'm basically getting the evolution matrix of qubit 1 at the corresponding time t. Again, U is the unitary operator that acts between time 0 and t. So that's one of the Raymond-Robichaud's approach. It's been actually recently published. Another approach, which is more general, and this is more what he conveyed yesterday in his talk, what he explained yesterday in his talk, is the so-called noumenal states. Now, I should stress that the framework in which Paul casts noumenal states is more general than quantum theory. It actually applies to any operational theories whose operations form a group. Quantum theory is one of them, and I'm interested in the quantum version of this. Now, how are noumenal states defined for qubit k? So again, the whole system I'm considering is n qubits. Let's see what's the noumenal state of qubit k. Well, the notation is insightful because it actually really is an equivalence class. It's defined as the unitary operator that the system has undergone up to unitary operations that do not causally concern qubit k. And so let me diagrammatically, if that's correct, write this as this object here. It's the unitary operator up to, what's this? Okay, up to what do not causally concern it. And so I titled that part of my talk quantum locality, and then one might wonder, well, Charles, you just told us 3 different ways of describing quantum locality. And so this is where I'm coming to unification, because I showed that these 3 apparently different approaches are in fact all equivalent to one another. In the sense that there exists a one-to-one mapping between each object. A descriptor of qubit k at time t defines a unique evolution matrix, which defines also a unique noumenal state of the qubit. Now, this equivalence is quite straightforward. I almost did the job by arguing so far. They differ by an operator basis. Now, one may say, well, here there's just 2 components, while here there's 4 components. Yes, but the multiplicative abilities of the Pauli matrices enable me to retrieve the sigma y and the identity, and so then I can change basis from one object to another. Now, the less obvious result is this equivalence. But I will not go to the details. Have a look at the paper if you're interested. Because in fact, you need to understand also the B's and the C's of the Deutsch Hayden descriptors. Now, yeah, let me move on to the cost of quantum locality. This was a puzzle that kind of attracted my interest during my doctoral thesis. I discovered those approaches to purely local quantum theory. And then I was like, well, it seems like the objects involved are mathematically big. Like they contain a lot of information. And so I'm going to state the results. And again, we consider an n-qubit network. I'm just repeating the same setting. And as a measure of cost or how mathematically big they are, I investigated the space dimensionality of the space in which the objects are described, or in other terms, just the number of degrees of freedom of the corresponding mode of description. So just as a warm-up, what I mean here, if I were to ask, what's the space dimensionality of the density matrix of a single qubit? Well, it's 3. There's 3 degrees of freedom that needs to be specified to specify uniquely the density matrix of a qubit. That's well known from the block sphere representation. And now another easy one that I assume most of you are aware of. What's the space dimensionality of the global wave function? In which space does this guy live? Well, how many degrees of freedom does it have? I need to specify 2 to the n amplitudes, each of which being complex numbers. So they contribute to 2 real numbers. That's 2 to the n plus 1 then. Minus the global phase, minus the normalization. And we have a space dimensionality of that for the global wave function. And now my puzzle was, well, what's the space dimensionality of the descriptor of a single qubit? How many real numbers are needed to specify uniquely the descriptor of a single qubit? And the answer I found was this: 3/4 times 2 to the 2n. So more than they are real numbers in the global wave function. And then I will come back to this. But just to finish the results, one may get feared that the global descriptor then is even much bigger. Well, it happens that it's not so much bigger. It's just 2 to the n minus 1 parameters to be described. So how do we prove this? In fact, showing the equivalence between numinal states and descriptors was the way for me to tackle this problem. So after showing this equivalence, then it means that descriptor of qubit k at time t is the same as the equivalence class defining the numinal state. Now that's a unitary operator up to some other unitary operators. Well, then the space of descriptor of a qubit in a network is then given by, I'm just repeating myself, a unitary operator up to another unitary operator, which acts on n minus 1 qubits this time. Well, this u is there for the Lie group. You know, it's the Lie group, u 2 to the n. Unitary operations on the Hilbert space of dimension 2 to the n. And you take a quotient with his little cousin, another Lie group. Since this guy is a compact Lie group, and that's a closed subset of it, the quotient manifold theorem applies. What does that mean essentially is that a Lie group is a group endowed with a differentiable manifold structure. When you quotient them, it loses its group structure, but it keeps the differentiable manifold structure. So it's well defined to be speaking of the dimension of this object in differential geometry, say. And that's given by the difference of the dimensions of the object involved in the quotients. And now a Lie group, the unitaries over 2 to the n has dimension squared of that. I'll leave you that to figure it out. You can just count the constraints and how we define a unitary matrix of the right size. And so the difference gives us 3/4 2 power 2 to the 2n. No, 2 power 2n. Very similarly, we can approach the problem for the global descriptors and get that the space dimensionality is this. Again, by the identification of the global descriptor with the global numinal state. Now, what's a global numinal state? It's a unitary evolution up to transformations that do not causally concern, this time not qubit k, but all the qubits, all the system. So that is just up to a phase. So it's basically u up to a phase. And so the space of global descriptors is given by this, which simply, when we compute its dimension, we get that. Now, if you are skeptical about my approach involving quotients of Lie groups and you would like to have a more down-to-earth argument, I won't make it here, but in my paper, there's an argument how you can, from the global descriptor, with a simple algorithm or like a computation, get U up to a phase. So you can get all the matrix elements of the unitary operator up to a phase. Go check it out if you're curious. Where does this leave me? There we go. Sam, can I know how much time I have in my whole 50 minutes?
Right. Let me see the time right now. So you have until 20 past 6, and it's now almost 6. So you still have another 20 minutes.
Okay, I'll try to
talk in the Q&A.
Okay. Yeah, well, yeah, exactly. I'll be dividing it. Thank you.
No problem.
Thanks. So let me just stress the huge difference between the density matrix of a qubit, just 3 numbers. We're happy to play with that. And the story I'm just telling you, which if you want to specify the descriptor of a single qubit, then one needs that amount of numbers. It looks like a terrible result. It looks like it's crazy. A first argument I want to make is that it was to be expected. Well, not precisely this number, but at least the exponential scaling. Any local and complete description must leave exponentially many parameters in each qubit. So at some point we have to choose what we want, right? If we wanted that, it's no surprise. Why? Because suppose you have your description of qubit 1, description of qubit 2, and so on, description of qubit n. And by completeness, you ask them to be able to spit out the distribution of any measurement made on the whole network. Well, that's encompassed by, say, the global wave function of the whole network. It could have been also its associated density matrix, but it's all the same. But we know that there's exponentially many parameters in this guy. So the most economical local repartition of those parameters in each system must still leave exponentially many parameters in each system. So I guess we should not be go monster under the bed about this, and instead we should find it interesting. There's one thought that I'd like to share is, if we consider the multiverse, then we have to be aware that whenever we write down, oh, my qubit is in the wave function alpha 0 plus beta 1, well, it's a lie. What I mean by this is that when we do that, we're kind of supposing that the qubit we've just prepared is completely unentangled from the rest of the multiverse. It's a useful lie when what we care to describe is just a subpart of the multiverse, and we make the assumptions that the other parts of the qubit will not interact with the qubit we're just prepared in a part of the multiverse. But as a multiversal object, a qubit is big. It's highly entangled. Now, this brings me to my final thought about the equivalent of the pictures, the equivalence of the pictures. I am not the first one asking the question. I'm quoting here Peter Barn from yesterday. The common misconception that the Schrödinger and Heisenberg models are equivalent to each other, they are not, Say told me repeatedly.
This iPad cannot connect to the internet.
I hear some sound. So,
yes,
is it the same for everyone?
So let's say,
watching movies and stuff on it before. Are they already downloaded?
Yeah, but right now there's no internet connection.
Yeah.
can we
It can
mute?
be
I'm
sketchy.
trying to,
But
yeah, I'm
we're
trying
not
to
getting
mute.
upgrades till next.
There we go,
Okay.
muted.
Thank you, Sam. Thank you. So I don't know what Zay taught, but the point is that it was a nice wink to Peter's talk here. But there's one way to see this: if we were the instrumentalist's glasses? Well, then the pictures are of course equivalent. What do I mean here is that for an instrumentalist, quantum theory is just a tool to help us make calculations and predictions, but it doesn't say anything about the real world. So if the only thing we're interested in here is sandwich-like computations like that, and we don't care what they say about the world, well, of course, we can get the use to act on the state or get the use to act on the observables. And then I'll go to an instrumentalist and I'll say, well, you know, in the Heisenberg picture, there's this cool object which can be separated into local systems. You'll go, well, I don't care. That doesn't mean anything because a theory is just there to make predictions. So I think we should remove those instrumentalist glasses. And there's another approach that I want to be addressing here is if we take a more constrained notion of what the Schrödinger picture is, which I think is still shared among us in our community, namely that all there is the universal wave function. If that's what one takes as a Schrödinger picture, all there is the universal wave function. So that's the description of reality for this constrained version of what the Schrödinger picture is, then we don't have an equivalence. Why? Because the universal wave function can be computed from the universal descriptor, but not vice versa. In fact, I argued that the universal descriptor is the unitary operator up to a phase. And in the right basis, the universal wave function is just a column of the unitary operator. Okay, if we have the Heisenberg state or the initial Schrödinger state, that's how it's computed. It's U acting on 0. But we cannot retrieve the unitary operator from just the state vector. So then that makes quite clear that when we understand, if we want to understand quantum theory in the Schrödinger picture, then, oh, sorry, a little wink with that would be the phenomenal world and the blue pill that Paul was referring to yesterday, whereas this is the noumenal world. So coming back to my idea, one should enlarge his vision of what the Schrödinger picture is. And it's not true that all that there is the universal wave function. The dynamics also matters. What that means is that this unitary operator that's responsible for the dynamics should be taken as intrinsically a description of the whole system. Now, I'd like to finish with a Nevretsian thought. Sorry. Everett argued that there is absolutely no need to have a boundary between a classical realm and a quantum realm. And he argued that if this idea is to be taken seriously, that we throw away such a boundary and that everything should be explained quantumly, well, then the world is much bigger than what we used to think. The world is given in Everett's idea, and so far as I have understood them, the world is given as the universal wave function, which exhibits patterns, some of which resembles classical-like worlds. But then the idea that I'd like to let you on is that if we are to take locality seriously, then the universal wave function needs to be enlarged too. And encompassed, if we take the Schrödinger picture, also the dynamics into the description of the whole system. Now in the Heisenberg picture, the dynamical part is automatically taken care of in this object, which factorizes nicely to describe systems locally. And I would like to end in advocating that also when viewing quantum phenomena in the lens of descriptors, many phenomena become much clearer. I'm kind of referring here to Vlatko Stock, who explained how phases can be seen to be completely local in the Heisenberg picture, in this way of thinking. And also but it's not apparent in the Schrödinger picture. So I think we should be seeking for good explanations, and I would like to advocate that more work could be done in seeing how it works with the Heisenberg descriptors. So on that, I thank you very much. I'll be happy to discuss. I want to hear what you guys think.
Thanks so much for the talk, Charles. Then now we're moving on to the discussion session, and for which we'll have roughly another 13 minutes, and then there will be a break of 10 minutes before Wallace's talk. And I see that Chris Timpson has his hand raised. Please go ahead and feel free to ask your question.
Thanks, Sam. I think Paul might have been first.
Right. Okay. So Zoom doesn't give me the chronological order of the hands. In that case, Paul, go ahead.
Okay. Well, okay. Thanks, Chris. Look, I'm not quite sure, Charles, how closely this connects with what you're saying, but would you say that if there's a locality, then your absolute elsewhere is full of macroscopic superpositions, because there are all sorts of measurement-like processes going on, which is sort of another way of saying no boundary between the quantum and classical, because macroscopic objects are only in definite states in our light cone in general, whereas in absolute elsewhere, they're, something like the Andromeda Nebula on my simultaneity hyperplane has evolved for 2 million years into this sort of extraordinarily big macroscopic superposition.
I'm sorry, Paul. I think for sound issues, I was really trying hard to understand what you said. I understood you mentioned stuff about macroscopic states.
Oh, okay. Can you hear me now? Well,
that's better.
Okay, perhaps I was too far away from the machine. So look, it's the idea, if there's locality, would you accept that in your absolute elsewhere, there are...
In my what? Absolute del square?
Well, in your, outside your future and past light cones. Sorry, didn't you? Okay. Space-time outside your future and past light cones, there will be massive macroscopic superpositions because there are all sorts of measurement-like processes going on. And so what I was saying is, could that, connecting with what you're saying about no boundary between a classical and quantum worlds, then there's a sense in which the macroscopic objects are only in definite states within your future and past light cones. And something, as I was saying at the end, something like the Andromeda Nebula, which I see now 2 million years away, on my simultaneity hyperplane now has undergone 2 million years of evolution into a massive macroscopic superposition. Would you agree with that?
I see no link between these claims about locality and any kind of macroscopicity.
Oh, all right.
All
right. Okay. So well, I mean, for a quick possible idea is, if I'm Alice, I've done my measurement, and I'm on one branch, and Bob's at space-like separation is doing measurement. He's gone into a macroscopic superposition for me.
Yeah, well, all this is again understanding the story through Schrödinger's state, and we are still very early as to what is the story in the Heisenberg picture formalism. Just this year has been published work on what even is a relative state in the Heisenberg picture. I'm referring here to Sam Kuiper's and Deutsch's paper.
Okay, so what I've just said sort of doesn't translate into your Heisenberg perspective. Is that right?
I don't see how directly, and maybe it's because I've misunderstood the question. If you don't mind, I'd like to move to perhaps another question, and maybe we can take it offline in the discussion.
Yeah, okay.
Then Chris Timpson.
Thanks, and thanks so much for your talk, Charles, which I enjoyed very much and agreed with an awful lot of. A lot of the terminology around these issues is contentious, as we saw a bit yesterday, and often some of the fighting is about terminology rather than substance. But we do need quite a lot of kinds of terminology, even if it doesn't matter quite which words we use for the various notions in play. So Lev yesterday, I think, was trying to urge us to distinguish between notions of dynamical locality, so doing something over here, not making a change to the properties and things over here, and contrasting that with what might be called a kinematical locality, or perhaps a separability, which is to do with whether or not specifying the intrinsic features of this system and this system are enough to specify the intrinsic features of the union of the two. So what's going on in the Deutsch Hayden approach, and as you've very helpfully explained, and as Paul explained yesterday in his approach, is that what one's getting is not so much to do with dynamical locality, though one has that for free because we're doing unitary quantum mechanics. What you're getting is separability. And why are you getting separability? Because, as you've nicely illustrated with these exponential sizes, is you're expanding the space of the intrinsic properties of the individual systems. So really what we face here is a trade-off between more intrinsic properties of individual systems against non-separability. So the standard Schrödinger picture, as I see it, says we're not too worried about non-separability at the level of the fundamental states of the theory, the intrinsic properties of the whole. The intrinsic properties of the whole aren't fixed by the intrinsic properties of the parts, non-separable, but in the Everettian context, dynamically local. Whereas what you and what David and Patrick Hayden and Paul are offering us is, no, just jump in, have a larger set of intrinsic properties of subsystems, and then you'll get away from having to have non-separable states. So I think that lesson is really important that people are aware of. And then it just comes down to, well, how much do you like separability versus non-separability? How do you want to weigh off, compare the costs and benefits of this large expansion of the intrinsic properties of the subsystems against the gains with respect to separability? So that's the question we face. And then, as with so many questions in theoretical physics, or maybe even worse in philosophy, it can devolve somewhat into a matter of taste. So my taste is more along the lines of, I don't see what's so bad about non-separability of states. We can live with that. For me, that's what standard Everettian quantum theory is. I think that's so for Lev as well. I mean, I like the fact that you can do this nice Deutsch Hayden construction. I've been interested in this for a long time, as David Deutsch knows. But
I've read your thesis.
Yeah. But that's the choice we face. And so the way I try and press, if I were minded to make a point larger than just this ecumenical one of recognizing that there are these distinct flavors of interpretation that one can go for, and what really do you care about, the way I would try and press the cost, as you put it, it's not just in terms of the exponential size of the state space, it's just another way of phrasing that point, which is that, as I see it, because we have that exponential size of the state space for the intrinsic properties of the system at the larger exponential size, there aren't going to be any, there are always going to be aspects of the actual features of the noumenal world, to use Paul's description, that we're never going to be able to determine by any observation that can be done after time zero. So there's a kind of underdetermination worry that enters.
Yes.
So I know that David Deutsch disagrees with me to some extent on this, but that's, as I see it, is the cost that goes with the exponential size. But really, it's a matter of paying, as always in quantum theory, pay your money and take your choice. How much do you dislike non-separability? How much do you dislike a certain kind of underdetermination in at least the time zero states? That's how I see it.
I understand. And I'd say I have two comments. first, as Sam introduced me, I love algorithmic information theory, short programs, Occam's razor. But then, should we then retreat into quantum solipsism and say that, oh, the minimalistic object is just inside my brain? And usually we make mistakes when we go there. I think theory should be weighed by their ability to explain things. And for me, the most striking, actually you contributed on that, if I remember well, in some chapters of your thesis, the explanation of quantum teleportation when seen in the Heisenberg picture is so much better. So that itself is an argument for it. And the fact that it needs more parameters, that would also have been an argument against Everett's idea. It says, well, hang on, we don't need all those worlds. Like I'm just caring about this table here, so let's just make it collapse. It's going to be smaller. That's one comment. Another one I'd like to make right away is I tend to realize also that there might be a bit of a Bell kind of not fallacy, but property in my measure of cost, as I'm counting the number of numbers, of C numbers. If you watch the way the story it is at the operator level, or as I think Dirac would put Q numbers, then right, the story is not so clear. Like, can we even speak of large objects?
Yes. Yeah. Also, the space isn't enlarged. The Hilbert space is always constant. And if you're using a Schrödinger equation, then you're kind of committed to having a unitary, right? Like
well, this is the other aspect. So I was talking about intrinsic properties of systems. That's one distinction we need. I forgot to say that, Charles, you're dead right that we need that dynamics matters, but dynamics is not to do with how things are now. Dynamics is to do with how things change over time. So another distinction that philosophers draw is between the occurrent features of systems, how things are right now, versus their modal features, or their historic or future-looking features, how they will be, how they were, how they would otherwise be. So dynamics is to do with the modal and the historical. It's not to do with the intrinsic. So the Deutsch Hayden formulation beautifully, sufficiently enriches the number of intrinsic properties of subsystems. That changes in the intrinsic properties of subsystems encode the dynamics, the modal facts and the historical facts about what the system has been subject to. But we don't need to agree that modal facts and historical facts always need to be represented in the intrinsic or current facts of systems. We might like it if they are, but we don't have to agree that they are. So we don't need to deny the importance of dynamics. We can just put it in its proper place as representing not about how things are currently are, but how they would change to how they are, and how they would have been if they were different, if they'd started with different initial conditions.
Charles, I'll give you the opportunity for a brief reply, and then we have to end the session, and we can move to a breakout room where we can discuss here.
Yeah, well, let's go to breakout rooms. I think we can discuss there.
Yeah, shall I? Okay, in that case, yeah, thank you for the talk again. I ask everyone to join me a final time in thanking Charles, and then I'll end the recording here.